Hi everyone, in this video here, I want to basically talk about this limit here, and we're going to explain limits in an intuitive fashion so you can understand what you're doing in Calculus 3 when you're taking these 3D limits and kind of how to think about moving along certain paths. So I'm going to put this function, our function is 2x squared y over x to the fourth plus y squared. It's more surface, I should say, but basically it looks like this, not that, over x to the fourth plus y squared. So you can see it's an interesting little curve. It looks like, you pinched fabric right at the origin, kind of. I don't really know. I mean, some cool things about this graph, nothing too spectacular. It kind of looks like there's like a parabola being pinched near the origin on either side in a reverse fashion. So kind of interesting. And the question that it's asking is, at this point 0, 0, right here, what's the limit as we approach that value from the left and right? And trying to solve this can be very challenging. Especially if you have no idea what you're doing. And maybe you do, you just maybe don't understand exactly what you're trying to do. So to visualize what you're trying to do, to prove a limit either exists or doesn't exist, we have to do a few things. So let's say we want to prove a limit's behavior, right? Does it exist? Does it not exist? Well, we can take two approaches. We can prove existence. I'm not going to even say, well, maybe it's important. Prove existence. So if we go this route, we need to prove that the limit approaches a value that exists called, let's say, value A. So that's one way. That would prove that the limit exists, right? That's going to tell us some behavior. If the limit exists at this point, it's a finite value, it works. However, let's say things are finicky, okay? Maybe you need to prove non-existence. Yeah, maybe that's probably the best way to put it, because I put existence. So we'll also say you could also prove non-existence. So the limit does not exist, stuff like that. And that's going to tell you something. So you can look at both sides. You can try to prove existence. Does the limit exist? Okay, I'm going to assume that it does. How can I prove it? And then we could also prove non-existence. So the limit does not exist. Find a contradiction. So let's say the limit for path 1. So I'm just going to put limit of the first path. That might be like some value A. But when you take the limit going another path, you get a value B. So imagine, right, in Calc 1, we went from the right and the left because that's the only paths we could take. If you found going from the left to the right and from the right to the left, you found different values, and you knew that the limit did not exist. It's the same thing here. And when we want to know limit behavior, we look at 2. Well, in Calculus 3, we're not dealing with a 2D curve anymore, right? It's not like x squared anymore, where we can, okay, look at the limit going this way and look at the limit going this way and see what the value approaches, because instead of it being 2D, now it is 3D. So I'm going to draw a little 3D surface here, right? Kind of like a snowboard slope almost. Okay, so imagine this is our surface in 3D, right? And let's just say I'm having a top-down view of this. So it would be kind of just a rectangle. Sorry, I seem to suck at drawing. Okay, and let's say we want to find the limit at some point. So let's say we want to find the limit as we approach 0, 0, the origin. Okay, this might be challenging if we want to go this first route to prove the existence, because remember in Calculus 1, we could look at the left to the right and the right to the left. But notice now you have infinite ways to approach this point. You can approach from the corner here and zigzag around and go like that. Or maybe you want to overlap this guy and go back and go like that. Right? There's a million ways to approach that point on the surface, and therefore the proving of existence, like we saw in Calc 1, is just not a feasible way to go about proving limit behavior. It might be more advantageous to prove non-existence. Let's say, in here I kind of laid that out, the limit of the first path approaches A, but the limit of the second path approaches B. And when A is not equal to B, so we know that the limit would not exist, right? It's like when you would approach like 1 over x, right? You approach positive infinity when you go the one way, but negative infinity when you go the other way. Let's say that when we approach the limit from the corner here, let's say this is our one path, you approach a value A, but when you take this path, maybe you approach a value B. And if you can find a contradiction like this, where the limit of one gives you A, but the limit of another gives you a different value B, right? Because these are not equal, the limit does not exist. That's exactly what we're going to try and do. We're going to look at this surface and go among different paths and see if we can get a different value when we plug in the limit. Okay, that's a lot of talking. Hopefully that theory makes sense. We're not going to prove the existence. We're going to prove the non-existence, right? It's just an easier way to go about it. You would need probably some analysis to prove this, right? Some proofs like this is a subset of this and blah, 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 blah. It's closed region. That's boring. We're not going to do that. Okay, now let's look at this limit. Okay, and let's use that. So let's just prove, the first thing you should always do with a limit is just plug in your values and see what you get. So we're going to plug in 0 and 0 for x and y. And hopefully you can see it's going to be 0 over 0. So this is bad. This is inconclusive. It doesn't tell us anything, right? Because 2 times 0 is 0. 0 plus 0 is 0. It's inconclusive. We need some other way. And you might be thinking L'Hopital's rule. Let's do L'Hopital's. You can't do that here. Unfortunately, you just can't. How do you do L'Hopital's of two variables? Pretty difficult to do. I'm not gonna lie. It's a challenging thing for sure. If you can even do it at all. I've never actually looked into that, but I would assume the answer is no. You don't know how to do it, and if you do, you're a math wizard. So instead of doing L'Hopital's, what we're going to do is we're going to change the path. So basically, what this limit is doing, x and y, when you need to go back to the graph, I'm going to write in two curves, y equals 0 and x equals 0, so just flat linear curves. What we're doing, and I guess I should have put, I can make a little function for this. Is this gonna work? That'd be really cool. Where's my point? Oh, here it is. So what's happening with this guy? I won't even try with the point anymore. What's happening is if you look at these two paths, what we're going to do is we're going to go from the x, the x equals 0 bar and the y equals 0 bar, and we're going to approach from both sides, and we're going to pinch that point to the 0, to the origin 0, 0, and we're going to see what is that value going to be. So as we do this, as we come closer and closer and closer and closer, we just see it's inconclusive. It doesn't tell us anything. So that's what the first path is saying. But now instead, let's just go from the y equals 0 or x equals 0 direction, because and I'll show you why this is different, because you're like, well, it's the same thing. So let's go from the path x equals 0. So we are restricting our movement to only be on the y and the z. So only the y and z can change. X is a constant 0. So when x is 0, it changes our limit. So let me go ahead and change this limit. Technically, it would be 0, y approaches 0, 0. But it's you can just think of it as y approaches 0, right? A 2D limit now. Plug in 0 for all the x's, because we're literally going to just restrict x to 0. X must always be 0, and that's the path we're moving along. We're just moving along that y plane, or that y line on the surface. So as y approaches 0, x would be 0, so we're going to have 2, x is 0. 2 times 0 times y is going to be 0, over x to the 4th plus y squared. X is 0, we just have y squared on the bottom. So what does this do? Well, when you would take a limit, you'd find this to be indeterminate. You would do L'Hopital's once, that would be still 0. You do L'Hopital's again, you'd get 0 over some number, specifically 2 factorial. So what this tells you, which is really interesting, is that this limit is 0. So let's go back to this. X equals 0. So you can see only the y is changing and only the z is changing. What we're doing is we're moving along from the left and the right, and we are approaching this point 0, 0. And we're finding that when we do that, the limit is 0, right? Hopefully that's pretty obvious to see. And there's no x deviation. Now what I want to do is flip it, okay? Now I want to look at a different path and see if we can find a contradiction. So let's say that now y is equal to 0, and we're literally just going to set y to 0. So this becomes 0, and that becomes 0. And you see it's a very similar thing when we write it all out. It's the limit as x approaches 0 from the left and the right, and it's going to be 0 over x to the 4th. And when you would take this limit, you do L'Hopital's 4 times 4 factorial. 0 over 4 factorial is 0. Let me draw a better 0. A 0. So we actually didn't find anything too spectacular here. When we travel along both of these lines on the surface, we're finding that we are approaching a value of 0. Nothing's really changing. Okay, so that's not a contradiction, right? What we want to do is prove a contradiction. Right? When we go one path and another path, we get different values. That's a Calc 1 idea of a limit. So what we're going to try now is something a little more abstract. And when you see stuff like this, don't be scared. Just try stuff. Try different paths. If you get one contradiction, that's all you need. You can you can plug in, let's say for y, you could plug in a function of sine. You could put sine of x in there. As long as you get a different value than 0, that proves it proves that the limit does not exist, right? Because if you don't get 0, well, that means that you're approaching a different value. And therefore, that is a different limit you're approaching, and the limit does not exist. Okay, pretty simple. What I want to do now is say, okay, what if I make, and you're not going to see this if it's your first time, let's say y is equal to x squared. Okay, look at what we're doing here. Y is now x squared. Well, we just plug in x squared for y. We're going to get 2x to the 4th over x to the 4th plus x to the 4th. That's going to be 2x to the 4th. And, of course, we're going to approach... and the way that you would write this notation is x squared approaches 0, 0. It's going to be 2x to the 4th over 2x to the 4th. And what happens? Do you notice anything? Well, this is just going to equal 1. Okay, because 2x to the 4th over 2x to the 4th cancels. Isn't that really shocking? Notice now, when we go across this path, we get 1, but at the other times we got 0. This gives us that contradiction we need to prove that the limit does not exist, right? We're going with this route, proving non-existence of the limit to show some property of the limit. So therefore, we show that two paths approach different values. That's exactly what we did here. When we go along x equals 0 and y equals 0, compared to x and y being x squared, moving along that path, we get 1. Okay, so because 1 does not equal 0, the limit does not exist. And if you're confused, I just want to clear this up. If you're confused why this works, basically what we're saying for the function is we have an input value of x. So our function starts with x and y, right? You plug in an x, you plug in a y, and when you go through the function, I should write it like this. Here's our function, f of xy. You get a z value out. So you plug in an x, you plug in a y, and you get a z. Another way that you could look at this is, okay, we get rid of the x, we plug in just an x, we then get a y, and we plug it in, we plug all this in to f of xy, or I guess technically f of xy, right? But we're defining y as x squared. So here's our little function box, right? The little machine. We plug in both an x and a y, right? But y is dependent upon x's value, and then we get out a z. So we're just changing it a little bit, but the process is the same. Okay, that's all we're doing here with this change, right? We're just saying that y depends on x now, and you're actually allowed to do that. So hopefully you guys enjoyed this. If you did, please drop a like, comment, and subscribe. Here's the full work if you want to look at it. But yeah, that's all to this limit idea. Hopefully you follow this stuff. I know it can be pretty challenging, Calculus 3, but you're strong. Stay in there. Love calculus. It's a great thing. And take care, guys. Bye-bye.